So good afternoon, everyone.
Good afternoon.
The last afternoon of the conference. Well, there's still tomorrow morning, of course, but I know that some people are already flying out today, so thanks for sticking around. So this is the second session I'm doing on In Memory OLTP. I did an overview on Tuesday. So who here attended the overview? Okay, so fair number, not everyone. Now don't worry if you did not attend it. So the overview I did on Tuesday, that was a bit of a why and a what is it. And this session is about when and where to use it. So in-memory OLTP is this really a kind of a revolutionary technology we built into SQL Server for optimizing performance of transaction processing. And if you've seen the demos, you see like really impressive performance gains that come from it. And I will do one of those demos later on as well. Now, the reality is, of course, this technology is not suitable for every possible scenario. Right? It's not like a magic go fast button. It's not the case, hey, you put all your data in memory optimized tables and all your queries all of a sudden run faster. No, that's not how it works. Its strengths are really like the core transaction processing, where you have a lot of concurrency, a lot of writes going on, but also a lot of other scenarios. So we'll go through that. So my name is Jos de Bruin. I'm a program manager in the SQL team, and I have actually been working on in-memory OLTP technology for about 4 years and a half now. I've seen it through first release was in SQL 2014, when we still had quite a few limitations, and it was like pretty difficult to use in many cases because of all those limitations. When I was SQL 2016, we made a big leap in terms of the feature set that is available for the in-memory OLTP technology. So it is now much easier to use and much easier to adopt in your applications. My contact information is on the screen, as you can see. Email, Twitter handle. Always, if you have any questions at any point in time, of course during the session now, please feel free to ask questions. And I would encourage you to use the mics in the room for the recording purposes. But if afterwards you have any questions, I will be here, of course, after the session. But feel free to reach out online also at any point. So what I want to do first is kind of a brief recap of what in-memory OLTP is, what it brings to the table, and then also talk a little bit about different modes of durability that are available in SQL Server, because there is an interplay between the performance, especially latency, and the durability, the level that you are using in the database. Then I want to approach the question of when and where to use in-memory OLTP from two angles. First, the when to use section will look at kind of what are the characteristics of a workload that you want to look for, where in-memory OLTP is either suitable or not suitable. And the second bucket is I want to go through a list of application patterns and actual customer case studies where this technology has been applied successfully. So you can look at those and see, okay, hey, this pattern looks pretty similar to what my application is trying to do, so maybe I should be thinking about using this technology. That's the goal. So let's jump into it. So first, a bit of a recap of what it is. So in-memory OLTP is a performance technology that is built right into SQL Server. But in some sense, it brings a whole new database engine into the SQL Server database engine. It was the data storage and transaction processing and data access methods were all built from scratch to benefit from the characteristics of modern hardware that is typically used for higher-end OLTP workloads. Modern hardware means plentiful memory and lots of cores in a machine, so a lot of concurrency. Where this technology gets its performance gains from, the three main factors. Number one is, well, if we assume we have plentiful memory available, we can just enforce the entire working set to be in memory. So we have this concept of memory optimized tables. The data is in memory. We know that it is in memory. So then the question is, okay, what is the most efficient way to store the data in memory, and what are the most efficient data access methods, right? So that is how we started. We did not look at what do the current data structures look like. No, we designed new data structures. And it turns out that you can build these data access methods much more efficiently if you know your data lives in memory. The second, lock and latch-free architecture. What does that mean? Well, if you have in high-throughput OLTP systems with lots of cores in the server, you will have a lot of transactions running concurrently. For example, a lot of sales orders being placed, a lot of bets being placed, for example. And all these transactions, they will try to access the same data structures, right? The same physical data structures. And with traditional data structures used for disk-based tables, there are several types of locking that are being used to kind of protect these data structures. There's spin locks, latches, logical locks. These are all used for several levels of protection. Now, we went out of our way to say, hey, well, actually, we don't really like this locking and latching, because that means you also need to wait a lot, right? If one transaction comes in, starts writing to a page, we'll take a latch, everybody else needs to wait. And we don't like waiting. We want every transaction to just go ahead and run, right? So we went out of our way to look at the latest kind of advances, even from 2000s, even 2010s, in kind of high concurrency computing. We applied those algorithms. We have a system now that is, for the core transaction processing, completely lock and latch free, not even a single spin lock. And this means that the workload scales incredibly well. That means the more CPUs you throw at it, the higher the throughput is that you can drive. Right? The only limiting factor here is basically the CPU. And of course also log I/O. And the third big factor is native compilation of T-SQL stored procedures. With native compilation, we take the T-SQL logic for the operations that you're doing and for your control of flow, and compile that down to native code, to a DLL, for the shortest execution code paths, right? The fewest number of CPU cycles. So we can get, with that, in some cases, an order of magnitude reduction in number of CPU instructions needed for a given transaction. That means that the transaction will need much less time to run. So it will run much faster. It will run, for example, in 100 microseconds instead of in a millisecond, right? And it is fully integrated into SQL Server. So you have the familiar T-SQL language, the same tools like Management Studio, SQL Server data tools, the same client drivers, always on availability groups, backup restore, it's all fully integrated. In terms of, well, the performance numbers, so we have seen with customers up to a 30-fold performance improvement, so it's 30-fold. Not 30%, 30-fold. And with one customer, bwin, or example I'd like to call out, they had an application where they needed to spread the load over 18 physical machines running SQL Server. Once they adopted in-memory OLTP, they managed to reduce that to a single machine. And in testing with that application, they managed to get 1.2 million requests per second run by a single server, 4-socket server. And this equates, in this case, because it was 4 kilobytes per request, and it was an update select workload, 5 gigabytes a second of data being processed, being ingested by the server. So in terms of features, then what does this look like when you try to adopt this in your application? Well, first, you have the tables. That is your base data structure. So memory optimized table. We have, this is the basic T-SQL table, how you write a table, right, in SQL Server. Now this option, memory optimized equals on, that indicates that this is a memory optimized table. So that is the main thing. So you can use your existing T-SQL skills or existing T-SQL examples for your tables. You just add your with memory optimized on. And then there's also this option durability, which I will touch on a little bit more detail later. But the default here is schema and data durability, meaning that every operation on the table is fully logged. Right? So it's, the operation, the change to the data is written to the transaction log, such as if there's a failure of the server and it comes back, your data is there. Then there are the table types used for your table variables and table valued parameters. Again, you add the option with memory optimized equals on, and then you get memory optimized table variables, which use the same memory optimized data structures as memory optimized tables do. And then we have, for the native compilation piece, the natively compiled stored procedures, which have the business logic. So this is your transactions, your DMLs, your selects, your control of flow. You have the keyword native compilation to indicate you want to use that. And similarly for scalar user-defined functions. So these are the two types of natively compiled T-SQL modules that we support today. Okay, then to come back to this durability option on the table, right? So durability, what do we mean with durability? So durability is one of the ACID properties, right? So ACID, the D in ACID, atomic, consistent, isolated, and durable. So durability is one of the key aspects when it comes to database management systems, right? Durable means that changes that you commit to the database, once a transaction commits, that change will survive server failover, server restart. And that is the guarantee that you get with any transaction in SQL Server by default. Right? You create a memory optimized table. If you don't say anything special, you will get one with full durability, meaning that any change to the data, once the transaction commits, you get an acknowledgement from the server, you know the data is durable, will survive, always on failover, will survive server restart. Right. Now, to make a change fully durable, what SQL Server needs to do is, well, when the client says transaction commit, then SQL Server needs to construct a log record in memory and needs to flush it to disk. So it needs to send that to the disk I/O subsystem. And this disk I/O subsystem can take some time to actually persist it. It depends, of course, on the quality of the disk, but the speed. But there is a potential latency bottleneck there. So it can, because of the log commit, the transaction as a whole will take a little bit longer, right? But still, this is in most cases really what you want to use, right? So in most cases, you don't want to worry about durability. You just use the default and you get your full durability. And also, usually the performance numbers we quote and the demos that we show are using full durability. So we are doing apples to apples comparison there. But we do have different levels now of durability in SQL Server. So in fact, the option delayed durability, this was introduced in SQL 2014. And delayed durability, this is a latency optimization. So with delayed durability, we're saying, okay, we're taking the write log to disk out of the transaction processing path. So you do transaction commit, and we don't wait for the log to flush to disk. The benefit of that is that there are actually two benefits. One benefit is that you get lower latency, meaning that the transaction finishes processing faster because you don't need to wait for the disk I/O subsystem. And the other benefit is that the log I/O itself is going to be more efficient, which means that you can achieve higher throughput. It is going to be more efficient because SQL Server can now more easily group multiple transactions together and, or rather, put their log records together and flush those to disk. Right? Of course, the con is you can lose some data. So it is usually not too much, usually just a little bit, a dozen kilobytes or 1 millisecond worth of data. But that is not a guarantee, of course. If your disk I/O subsystem is not keeping up, this can back up to about 8 megabytes at the moment, something like that. So this is not for everyone. Right? This is for applications that can cope with a certain minimal amount of data loss. So if you have, for example, in your app, if you don't care that much about every record, for example, but you want records to be generally be processed very fast, this might be an option. Also, if you have the data elsewhere in the system and you can retrieve it in case there's a failure. So there are architectures where the data goes through multiple layers. For example, if you think about placing orders on stock markets, typically in most architectures, they will go through several layers of some validation here and there. So the data will still be somewhere in the system. You can still retrieve it if there's a failure. And also, one thing that I have heard from already quite a few customers, what they ask me is, hey, I want to do always on. I want to have automatic failover with async replicas. Right? Asynchronous replica meaning that on primary commit, you don't wait for the secondary to come back. Right? So there's also potential for data loss if you have failover there. So by default, so we don't actually support that scenario, having async secondaries with auto failover, because if a failover does happen, you can get data loss, right? But still, if you're fine with data loss, with some data loss, you can actually configure an always-on availability group with sync replicas and use delayed durability, and then you get very low latency because you don't wait for the data to be replicated to secondaries, but still automatic failover. And again, use this only in scenarios where you know you can cope with some limited data loss. And finally, we have the non-durable tables. So these are tables, these are memory optimized tables that are specified with durability equals schema only. That means that the data in this table is not persisted at all. So there's no I/O for any modifications to the table. So that means very low latency, obviously. But it does mean you lose all the data on failure. This means that it is only suitable for certain scenarios, for certain, especially transient data scenarios, where you have some data that you need to cache for some reason, and it's okay if you lose it. Maybe you use it for something like a session state. You just require users to log in again, create a new session, or you use it as for mid-tier caching, and then you can just rehydrate the cache. Right. Okay, so I want to show you a quick demo here. Unfortunately, I need to log in again on my machines. So the demo I'm going to show is actually this application will look familiar to probably to many of you. So I will just quickly show what performance benefit this app has for with in-memory OLTP, and then I will go through these different durability options. Right? What is the impact on the workload for that? So this app, to briefly recap, it simulates a high volume OLTP application. In this case, it simulates ticket reservations. So what it tries to do is it has a bunch of connections, like 80 connections, and each connection is trying to run transactions as fast as possible, right, in a loop. And we are really taxing the server with that. So this is the highest throughput we can get with traditional disk-based tables with this workload. Now, if I change my table and my stored procedure to be memory optimized and natively compiled, so I have here my memory optimized table, and I have here my natively compiled stored procedure. So I'm going to apply those to the database. I'm just dropping my old table, creating new memory optimized, dropping the old stored procedure, creating new natively compiled. And when we go back here, we already see a pretty nice performance gain. This is, of course, a demo scenario, but yeah, still, this is like a kind of potential that you can see already about almost 50-fold, right? Now, one thing to notice here is that this profile, the performance profile after migration, looks a little bit jagged. I mean, it really stays up there, but it's a little bit jagged. Now, to me, this is often an indication that log I/O is a bottleneck here. So what I can do is try to remove log I/O as a bottleneck. So in this case, what I'm going to do is I'm going to apply delayed durability to this database. So you can do it. You can apply delayed durability at the transaction level, at transaction commit, or at the database level, where you can force every transaction to be delayed durable. And that's what I'm going to do here. So as a database option, I will go to the properties of the database, go to the options, and of course you can do this in Transact SQL as well. Let me center this a little bit here. Okay, we scroll down. Whoa. And we have here delayed durability. So by default it is disabled, right? Because you don't want people by accident to use delayed durability if you're not asking for it. But in this case, I'm going to set it to forced. So forced means that every transaction is going to be delayed durable. Okay, and we'll start this workload again. And you can see that the throughput is now actually a little bit higher because we remove the transaction commit out of the critical path, meaning that now log I/O becomes faster, and well, there was still a little bit of a dip, but in general, the performance profile looks a bit more solid than it did before. Now, what I will do next is I'm going to throw caution all out the window, and I'm going to go completely non-durable. So this is obviously not something that you would do for a usual transaction processing workload, because I could lose all my data if there's any failure, but just as an experiment for this workload, I'm going to try it. And there are like caching workloads often have kind of a similar pattern, and for caching workloads, these schema-only tables are very suitable. So this could be a reasonable representation of a workload like that. All right, so I made my table now schema only, so I configured here durability schema only. And let's see what is the impact on my performance. So I have another jump in performance, right? So this is all going all the way up to 54, 55 times the original performance I got with the disk-based tables. So to summarize here, so we started off with traditional disk-based tables and traditional stored procedures, and this scenario actually has a lot of latching and latch weights in there. So there's a lot of concurrency and a lot of waiting because they all try to access the same data structures, right? That is why I'm seeing such a big jump in performance when changing the table to memory optimized, and in this case I changed also the stored procedure to be natively compiled because I want it to be as fast as possible. Then to go one step further, see what is the impact of delayed durability. We saw that when making all the transactions delayed durable, we saw even another bump in performance. And then when making all the tables fully non-durable, so making them schema only, we saw even a bigger jump. So with this, this is going to be like completely CPU bound. We're not doing any kind of I/O anymore, so we're not spending any cycles on that. So this is really the highest throughput. If you would see the CPU profile for this, you would see would pretty much be pegged at 100% CPU. Okay. Yes.
Yeah. So you discussed always on and delayed durability. What if I had a bank of session state databases and a network load balancer in front that I wanted potentially asynchronous, always on across? Could I use a schema only with asynchronous always on?
So the question is, I would like to have like a session state database in always on configuration with load balancing. Can I do that with schema only tables? The answer is no, because replication in always on availability groups is based on the log being generated, so you would need to use schema and data. I will say that with a single server for sessions, you can get the 1.2 million requests a second that we saw earlier. So for many applications, that is going to be plenty. Okay, let's head back to the slides. Okay, so when to use in-memory OLTP? So I want to go through some application characteristics that you would want to look at to decide whether or not this is probably going to help you. Right. So we'll start with the yes column. So if you have some of these characteristics, yes, you should probably be considering in-memory OLTP. And this is like more kind of high-level characteristics. We'll also talk through some of the more lower-level characteristics. So if you have a transaction processing workload and you really need to increase the throughput, right? You have a demand from your customers to have higher throughput in a transactional workload. You need to place more bets per second, so you need to place more market orders per second, for example. Improve data ingestion rate. So you have, as an example, a lot of sensors in the field. You have an IoT application, a lot of sensors in the field. You want to ingest that data. You have more and more sensors that are being deployed. You get bigger customers. You need to improve data ingestion. Also, you want to consider this. Reducing latency. So if you are very latency sensitive and your bottleneck is in the database, right? You want latency here means the time it takes between request coming to the database and completing the request, including transaction commit. This technology will really help you. Another one is consistent low latency, because there are applications that have like spikes in workload and then corresponding spikes in latency, and they are often not acceptable. Like even if today your average latency is okay, but once in a while you see a spike that you cannot really cope with, then again using in-memory OLTP, completely log-free, you will get rid of your spikes. Then there are the transient data scenarios with your schema-only tables, your caching, your session state. We've seen it's very suitable in those scenarios. Now, when don't you want to consider it, right? When is it not a good idea to use this technology? Because I have actually heard from like many customers who just try to put their tables in memory, make their tables memory optimized, and then expect the query that was running slow to run faster. That is probably not going to be the case. If it's a single simple select statement, it's probably not going to run faster. Right? You need to look at the workload as a whole. So especially if this select statement is going to do like big table scans or do aggregation across a lot of data, that is more of an analytic style or BI style query. And in-memory OLTP is not really the technology that helps to optimize that pattern. So for that, you want to consider column store technology. If the performance bottleneck is outside of SQL, so in-memory OLTP optimizes the transaction processing that's done in the database engine. But if in your workload you spend a lot of time in, for example, in network traffic, going back and forth to the server, and you spend only like 5% of your time in the actual transaction processing, well, we can make that maybe 1% or 0.5%, but for your overall performance, it's not going to be that big of an improvement, right? And that is especially with a pattern we call chatty applications, which are applications that to do one business transaction have a lot of back and forth between the client and the server. I hear of applications that, for example, to render a single screen to the user, do hundreds of calls to a database. Right? That is very chatty, and with that pattern, you spend most of your time in the network stack, not in the actual transaction processing. So you should first push down your logic into the database, and then in-memory OLTP will be able to help you. Of course, if you have a low transaction volume, it's probably not really worthwhile to look at this. And also, you need to consider resource limitations, right? Because these memory-optimized tables, your core transaction tables, they do need to fit in memory. So you need to have enough available memory on the server. If we go one level deeper to look at, okay, what are exactly the operations that we can optimize, and what are the weights you want to look for. So insert, update, delete operations, they are always faster with memory optimized tables. So the way in-memory OLTP was constructed, it really optimizes the DML code paths. So those operations are going to be a lot faster. If you have a high degree of concurrency, you see in your system a lot of concurrent requests running at the same time. Probably you want to consider this. If you have latency spikes, you see during your spikes that you have waits on latches or locks. Consider this. Again, transient, temporary data. Even if you extensively use something like temp tables, table variables, also look at this. And also if you have actual bottlenecks in TempDB. So for highly concurrent OLTP applications that extensively use TempDB, there's often contention on allocation resources like PFS or SGAM pages. And if you are using Azure SQL Database, then you should consider that the actual activity in TempDB also counts towards your resource limits. So when you use in-memory OLTP, you make these operations more efficient. So with the same pricing tier in Azure SQL Database, you can do more operations. It also helps in reducing log throughput because index operations are not logged for memory optimized tables. So this will help you there as well. Then if your data is temporal in nature, meaning that there's like a historical aspect to it. For example, you have sensor data, you have your current readings, and you have your historical readings. And there's a nice pattern with temporal. I will talk about that in a little bit more detail later on, where the current state of affairs is maintained in a memory optimized table in the current table, the current temporal table. The history is maintained in a disk-based table. So the nice thing is you only need to provision enough memory for the kind of current state of affairs, and the management of the data, the movement of the data from memory to disk is handled by SQL Server. Then specifically about when to use natively compiled stored procedures, because this can also be kind of tricky, because natively compiled stored procedures, they are also not ideal for every scenario, but it's more if your stored procedure looks a bit like this, then probably native compilation is going to be a good idea. So so the DML is going to be faster. If your queries touch a limited number of rows, so if you do full table scans of multi-million row or billion row tables, native compilation is not going to be good for you. But if you touch a limited number of rows, for example, you process a sales order with corresponding line items, those types of operations, their native compilation will work very well. And also, the more logic you actually have in the stored procedure itself, the more native compilation will help, because the more logic you put in the procedure, the more we can optimize. Right? Now, when not to use, so if your query plans show like large scans or large table scans, large range scans, and need to use column store instead, if you have a slow log I/O device with short transactions, so we have seen this actually with quite a few customers who have been testing this technology, and they tested this not on their production hardware, but on their desktop with spinning media, and they were not seeing any performance improvement. But then it turned out that the log I/O was the bottleneck. So so much more time was being spent in the log writes than in the actual transaction processing. But for those scenarios, actually delayed durability would really help. Of course, if your tables don't fit in memory, cannot use it. And yeah, so if you have these analytic style queries, when you think about native compilation, but you have analytic style queries, then you're better off using traditional stored procedures. So queries touching large numbers of rows, queries that run in parallel today because parallel execution is not supported for native. Those you want to use traditional stored procedures. Okay, so let's look at the other angle. So that was a bit about like what are the characteristics of your workload you want to be looking at. But now let's look at a kind of a higher level at application patterns and actual customer scenarios that we have worked with And then we have seen customers be successful with this technology. So this is the list of scenarios I want to cover. And I have details on each of these. So high throughput OLTP, that is kind of the core scenario that we had in mind when building this technology. So that is where you have a lot of transactions happening at the same time, and you need low latency. Shock absorber for data load. So shock absorber, that refers in this case to spikes in the data being generated and the data that needs to be ingested in the database. Internet of Things is like where you have like devices, either like consumer devices or sensors in the field, sending data over to the database, and you need to process that data before you can do any reporting on it and do any analytics on it. Then session state and caching. So session state is in some sense a special case of caching. So you cache some data and you don't really mind losing it too much. Sorry, I'm a little bit too fast here. TempDB replacement. With TempDB replacement, I mean leveraging some of these memory-optimized data structures, like memory-optimized table variables, memory-optimized tables in the schema-only mode, to replace like traditional table variables or traditional temp tables in existing applications. It is often kind of a low-hanging fruit. So with minimal effort, you can often get, well, depending on the application, but you can often get like good performance gains. ETL is another interesting scenario. ETL stands for extract, transform, load. So that is often used in data warehouse settings where you have data flowing from operational systems into the data warehouse, and then there's a transformation process as well. So for those, the recommendation is to use schema-only tables as staging tables. Okay, so let's get into some more of the detail. So high throughput OLTP with low latency. So actually, I would say this demo I showed earlier, where you had these transactions, these ticket reservations being placed, that would be an example of such a workload. Right? Of course, it was a very simplest example, and the actual customer workloads are going to be much more complex. And also, the actual application architecture might look very different from customer to customer. So I don't have an actual architecture picture for this one. But where we have seen this being used successfully, especially in terms of verticals, it's like in financials. Think about trading, like trading financial instruments, currency exchange. That is, there are quite a few customers leveraging in-memory OLTP to speed that up. Also gaming, betting. There in gaming, there's usually a lot of people like playing a game or placing bets on sports. And we have a lot of customers, like, for example, Derivco, leveraging this technology. Ad delivery as well. So you think about high throughput OLTP. So if you have really a high throughput, these are customers often with high throughput needs. So we have in testing, we can see with like a kind of more sophisticated order processing workload up to 360,000 transactions per second on a single server. And many of these customers, they come to in-memory OLTP when they see with their existing application that they reach some scaling bottlenecks. Right? So, for example, latch or lock contention. And you don't run into these bottlenecks with in-memory OLTP because it's completely lock and latch free. And there are also customers who build new applications and they see they have this kind of pattern, right? They have, for example, financial trading. There's one customer who does financial trading, who does currency exchange. They built a new application and they saw, okay, this is the high performance technology for OLTP, so I'm just going to build my application like that. So for new applications, in-memory OLTP would definitely be recommended if you are looking for kind of high throughput scenarios like trading, gaming, betting. Right. Low latency. So So there are applications, of course, that have extreme low latency requirements. So, for example, so actually both financial trading and sports betting are good examples there because, well, in financials, you have events that occur on the financial markets, right? And they occur very fast, and then people want to place their orders very fast following the event because things can be very fluid. You don't want the order to go through when already there has been a big price drop or big price increase. Right? Another example in sports betting is, well, you can actually place a bet on when somebody, in tennis, when somebody is about to serve the ball, you can bet on whether this is going to be a fault or not. And you need to process this pretty quickly because between the time that the serve starts and the time that the player hits the racket, that's not too much time, right? So the orders need to go through in that period of time. So consistent low latency, I actually have these examples for low latency listed here. So this is, again, good examples in both financials and in betting. So what can happen if you have in financial trading, financial instruments, there is an event happened on the market. There is some news from a big company or the Fed announces like interest rate cut or increase. That will prompt a lot of orders being placed, either sell or buy orders being placed at the same time. So there's a big burst of activity. And with traditional tables where you have your latching and locking, you will get these bottlenecks there. You get contention, and this results in waits, right? So I had a customer quoting me that saying that, okay, normally these transactions take 10 milliseconds, but I have spikes of up to 200 or 500 milliseconds. So I cannot meet my SLA anymore. This takes too long for my customers, right? So with in-memory OLTP, what they can do is they will always guarantee this consistent low latency because every transaction will just go through the system and does not need to wait. So yeah, to get started with this, well, either you can just, if you build a new app, you would just make all your tables, transactional tables, memory optimized. And if you have some historical data, you would put those in disk-based tables. If you have an existing application, we have tools in Management Studio to actually pinpoint the tables and the stored procedures that you would want to consider for migrating to in-memory OLTP. And the shock absorber for data load. So this is an example from one customer, but there are actually quite a few customers who have a very similar pattern. So in this scenario, this is from Beth Israel, which is a big healthcare company. They need to log security events coming from their Active Directory domain controllers. And that is used to kind of assess unusual activity in the system, right? To try and detect breaches and unauthorized access as well. So these events that are generated by the domain controllers, they are ingested into the database. And before in-memory OLTP, they went into a disk-based table, like a kind of a staging table, and they had a regular process to move these tables, or move the data rather, over to their permanent storage and do some transformation along the way to actually extract the data, put it into proper format, into columns that you can actually run a query against. And they would run then the reporting queries against it to try and detect this unusual activity. They have about 5 million messages a day. Now, what happened was that if there were bursts of activity, this would lead to delays in getting the data into the database. So a database could start running behind, actually, and if there are these bursts. Another issue was that there was a lot of latch and lock contention when doing this batch transformations from the initial staging table to the final table, to the final event details table. So as a result, they could run this batch process only once an hour. And that resulted in a large data lag for their reports. They want to be like very close to when the kind of security incidents actually happen, because if you detect the breach an hour later, that it might be too late and all your data is already gone, right? So they want to have this in near real time. So what they did is actually migrate this staging table, the events table, to a memory optimized table. And that is used to ingest all the data, and for the events detail for the final table that has all this kind of historical data, they're using clustered column store because that table is used for analytics. And they now do a regular batch movement with transformations from the one to the other, and they can now run it every 5 minutes. Well, actually, they do run it every 5 minutes, but they could run it faster if they would want to, but 5 minutes is good enough for them. So some of the benefits that they're seeing, so there are no longer any delays when there are bursts of activity. There are no longer any delays in getting the data into the database, so you can handle really high spikes in the workload. In the batch processing, well, they can run it now much more frequently, and they can actually run it faster as well, especially with some of the native compilation improvements in SQL 2016. And then finally, they also achieve higher query performance in their reports because they're using clustered column store. I know it's not specific to in-memory OLTP, but this is a pattern that we think can be used pretty often, where you have a memory optimized table as a kind of shock absorber to absorb spikes in the workload, with the batch offload to clustered column store. And the clustered column store, because of the compression, has a smaller on-disk footprint, and because it's optimized for analytics, your reports run very fast. Yeah, so and now they can run their reporting in near real time, which is like the main requirement. So they can really fast, they can detect if there are any anomalies in the environment. This is also a shock absorber example, but it is slightly different. So what we have here is this is a kind of a retail scenario where we have a kind of an aggregator of inventory information, EdgeNet. They aggregate inventory information, maintain inventory information and pricing for physical stores of some large retailers. And this is used both by internet search and also mobile applications. And the data is really read mostly. So most of the time, the access is trying to read the inventory data. And what happens is that, well, it does, of course, need to be updated once in a while. So the big retailers send updates of the inventory once or twice a day. And this then results in like pretty much an update of the entire table. So and they actually want to be able to do this faster, right? To react faster to changes in inventory. But the actual update with disk-based tables would take 14 minutes. Would take a really long time because of all kinds of contention. And also because of the contention, the latching and locking during the data load, the queries would run very, very slow. So in fact, from a query workload point of view, the data would not be available. So they actually implemented a mid-tier cache to mitigate that. They would cache the data there and refresh that cache after the data load finished. So with memory optimization, what they did is just change the table. They had a single table, change that table to memory optimized. With that, the time that it takes to do this batch update of the entire table is reduced by a factor of 10. So it was reduced to 4 minutes. So they can run batches much more frequently, every 4 minutes in principle. And the nice thing there also, because it is log-free, so you don't have any impact on the read workload, on the select queries, while the update is happening. So they could actually, and they actually did, remove the mid-tier cache. So they really significantly simplified their architecture of the application. Okay. So the next scenario I want to talk about is IoT scenario. I have two IoT examples here. So the first one is a cybersecurity example. I cannot name the actual customer here. But in this example, this was a new application. And the key requirements are listed here. So want to ingest about 100,000 messages per second. These are generated by machines on the internet. And the other core requirement is to be able to perform real-time analytics over the last couple of minutes of activity, right? To see whether some real-world actions that had been taken, where they have any impact on the messages that are being received, right? What kind of impact there is. And then also the data needs to be retained for later offline analysis. So the architecture that they came up with is roughly like this. So they have two paths. The left path is for the real-time analytics. The right path is for the long-term storage and offline analytics. So in-memory OLTP is used on the left path. So they use a schema-only memory-optimized table. And this data is ingested in there. This is running in a single VM in Windows Azure. And then and because the data, so this database can easily keep up with 100,000 messages per second. And then because it is ingested into a SQL database, you can very easily run a query to get your data out, right, and to get analytics. You could ingest it in Hadoop. It's also being ingested in Hadoop or Azure Table Storage. I forget which one. But then if you want to get your analytics, your insights out of that, you need to do a lot of batch processing, and this takes a lot of time, so there's a lot of lag, so you cannot do real-time analytics. But because this is being ingested into a SQL database, they can do real-time analytics, and they can see immediately what is the impact of the actions that they are taking. So yeah, they evaluated a whole bunch of options, including lots of NoSQL options. They could not get that to work. Only with SQL Server with in-memory OLTP, they could achieve this throughput with real-time analytics. The second example for IoT I want to give is in the oil and gas space. So this customer provides a service to their customers, which are oil producers, to monitor and analyze their oil platforms, or the oil producing facilities. So these facilities, they are equipped with all kinds of sensors in lots of places. Like, for example, how full is your storage tank? Is this valve, does this look okay? Those kinds of things, right? You need to know, you want to be, for example, alerted when the tank gets too full or when there's a fault somewhere, right? And also some historical analysis. So they wanted to use a SQL database because then they could do this kind of real-time reporting and historical analysis. And they are like a cloud-first app, so they're using Azure SQL database in this case. But also there is pressure from their customers to keep the prices down. So they want to have a cost-effective way of doing this, right? And they were previously using disk-based tables, and they saw, well, the CPU and the log I/O were getting kind of high, and they might, to further grow, they would need to increase their pricing tier, would need to start paying more, right? Now the solution that they came up with is roughly like this. So you have all these sensors sending their data to mid-tier application hosted in Azure. That mid-tier application is sending the data to SQL Server, or rather to the Azure SQL database, using, it is packaged up, batched up in memory optimized table valued parameters, then being processed by natively compiled stored procedures, and being stored in a memory optimized table. And in this case, the memory optimized table is a temporal memory optimized table, meaning that only like the current state of the sensors is kept in memory, the history is kept on disk, and this process of moving from memory to disk is managed by SQL Server. And this also allows them to keep the footprint in check, the memory footprint rather. So they managed to reduce CPU through the use of TVPs for the memory, because of memory optimized table access, because of the native compilation. Right? They reduce log I/O because, well, memory optimized TVPs don't incur any log I/O. Traditional TVPs do in TempDB, and you have more efficient logging. Right? And with temporal tables, they managed to limit their in-memory storage footprint. So I have actually a small demo of this kind of IoT scenario. This is not exactly their code, but it is a very similar kind of scenario. So the scenario for this demo is going to be a smart grid. Let's see, I got disconnected, unfortunately. Okay, let's see if we can reconnect here. So we have sensors. In this case, in this scenario, we have meters at people's homes sending electricity readings back to the database for kind of further analytics purposes. This example is available on GitHub as well. Link is in the deck. So let me start the data generator. So what this is just, again, a workload simulator, yet another workload simulator. So this simulates 1 million meters that are all sending data to the database. And this is ingested into temporal memory optimized table. So we can look at what this is like. Let's see, which database was it? Power consumption, okay. So if we look here at the table, we see here the dbo.meter measurement system version that indicates it is a temporal table, so a table maintaining its own history. And we have this history table here. And if we look at the properties, let's zoom this out. Look at the properties of the meter measurement. Here we can see that this is memory optimized. Right. And if we actually look at the properties of the history, we can see that this is actually not memory optimized. So this is disk-based. Right. Okay. So I have this workload running, and what it does is it calls this particular stored procedure. Let me show you the stored procedure as well. Insert meter measurement. It just takes a batch of meter measurements from the mid-tier application that's essentially aggregated from the sensors. And for each item in the batch, it tries to update the sensor reading. And if the sensor reading did not yet exist, it inserts. Right. So there's going to be a total of 1 million sensors, and each has like continuously updating readings. So let's look at the data here. So first thing I'm going to do is look at how many rows I actually have in my meter measurement table. I have 1 million, so this corresponds to the 1 million sensors. And this is like this. The data in this table represents the latest sensor reading. Right. To make this a little bit more visual, let me also show you what the actual data looks like. Right. So we have here a meter ID that's like the primary key, and we have the actual measurement, the postal code it corresponds to, and the date of the measurement as well. Okay, but now I have of course all this historical data as well. So now I want to see, okay, how many historical readings do I have? So I use here this syntax for system time all, which looks at all the historical readings as well. So both the current readings and the historical readings. So I have a total here of about 14 million sensor readings. Another interesting thing I want to look at is what is my memory utilization, right? Because memory, if I am memory constrained, then this is going to be a valuable resource to me. So I want this to be kept in check. So we can see we actually have 2 memory optimized tables here being reported. So the first one is my user table, meter measurement, has only about 88 megabytes. 88 megabytes, that is a pretty reasonable, kind of small number, right? But it's only 1 million rows, so that's pretty good, actually. And then I have my memory optimized history table. Now, I told you earlier that the history lives on disk. So why is there a memory optimized history table? Well, it's there for performance reasons. So when you do an update of a row, we need to insert it to the history table at the same time. And if we were to to go directly to the disk-based table at that point, that would slow down the entire operation. So we don't want that. We want to deal in the online operations. We only want to deal with memory-optimized data structures. So this table is essentially the hot tail of the history. So when we update the current row, we insert under the covers, we insert into the history, into the memory-optimized tail of the history, and we do a regular batch offload to the disk-based history. So if I execute this again, you can see that this is kind of fluid, right? So actually, right now, the footprint of my memory-optimized history table increased to 304. And do it again, increased yet again a little bit more. Now, why does it keep increasing? Well, there is an asynchronous batch offload process. So once this fills up with 1 million rows, then we start the batch offload. So if I run it now I ran it again, and now we see it's back down to 22 megabytes, this hot tail. So you can see that this is really fluid. So the system is kind of working with the data. But the overall memory footprint is really being kept in check. It did not go much above 400 total, right? 400 megabytes, which is really very modest. So this is generally a recommended pattern. If you have sensors you want to ingest into the database, use a memory-optimized temporal table, and probably use a clustered columns or index on the history for efficient analytics purposes. Okay, let me stop that here, and we'll go back to the slides. So when you download the deck, there's links to the actual to the binaries and also to the actual source code, so you can play with this and use this to help model your application. Okay, so session state and caching. Another important scenario. Actually, many customers are using this technology for that purpose. So ASP.NET session state. So ASP.NET is, of course, the kind of web front-end technology that comes with .NET. And what you want typically in web applications to have the web service, the front-end service, to be completely stateless, so you can scale out very easily because they need to do a lot of their own compute. But the session state still needs to be stored somewhere, right? Because different requests from the same user can be served by different front-end servers. So SQL Server is a typical target for that. And these session states are stored as blobs in SQL Server, right? Now, what is also characteristic here is that sessions are kind of transient. If there's no session to be found, then the front end will decide to create a new session, right? So we'll just ask the user to log in again. And also, another characteristic here is that the number of sessions tends to be limited. You tend to not have like 1 million concurrent users really active on your website, maybe 100,000 or maybe less, depending on how successful your website is, right? So the session count is actually limited, and this is very update-heavy workload. So update-heavy workloads, in-memory OLTP usually performs really well for those. And there are also other caching scenarios, like simple key-value pairs, where you just, similarly to ASP.NET, where you just have your mid-tier app just wants to store some stuff somewhere temporarily. Yes?
So given your session state limitation, what would happen in the event of a DDoS attack against your web end front servers? Does it just blow out the memory on all your session state?
So the question is, in the session state scenario, if there's a DDoS attack against your web servers, would this blow up your memory footprint? I honestly don't know how ASP.NET reacts to a DDoS attack and what it does in terms of creating new sessions. I have heard from, we have quite a few production customers with ASP.NET, and I have not heard concerns around this. So, yeah. Okay. So in terms of other caching scenarios, so besides just putting a blob there of data, you can also think about like having some semi-structured data like JSON in there, using new built-in JSON functions that we have, or even a full relational cache. You want to cache tables or like rows with attributes, you can just store them in tables, right? So this is generally then roughly what the architecture would look like. You have your apps or your web servers that are interacting with the SQL database. And this one has memory optimized tables and for the cache items, Usually for just blobs, you would have like an integer or GUID identifier with then a blob column, so a var binary max column for the actual data. And you use native compilation for making this fast, the lookups of the cache. The results that we've seen is more than 1 million requests per second on a single 4-socket machine. bwin, the customer with this scenario managed to reduce their SQL Server footprint from 18 servers to 1. And they are now also actually in the process, or they have already implemented a caching solution for their entire enterprise, where they have hundreds of applications that all need some kind of caching. They used to have all different kinds of caching solutions throughout, and they wanted to standardize into one to make the IT landscape simpler. They evaluated a lot of alternatives, including some NoSQL alternatives, but based on their previous experience with ASP.NET, they decided, hey, let's look at this technology for our caching needs. And they see that they can get much higher performance than any other caching solution with much less hardware, because for any NoSQL solution, they would have needed to provision a lot more hardware. And they get, for the requests to the cache, a consistent latency of under 1 millisecond for every application. Okay, let's go to the next one. So this is the scenario of the TempDB replacement. With TempDB replacement, I mean you don't actually physically replace the entire TempDB. I'm talking about replacing some of the user objects you have in your database that are currently leveraging TempDB, replace those with memory optimized variants. So first, let's look at traditional TempDB-based table variables. So here we have a mid-tier application, a user database, and we have TempDB, right? So in this case, the mid-tier application invokes a stored procedure. For example, as an example, I'm going to insert a sales order, right? And then because I have a number of line items, that is not a fixed number, it is variable between requests. So I'm using a table valued parameter for that, which is the typical way you would send data to the server in this kind of scenario. So what happens then under the hood is we actually create a data structure inside TempDB to represent this table valued parameter for further processing, right? And this is where some concurrency bottlenecks actually also come in. A lot of allocation needs to take place. So each table valued parameter has some corresponding allocations that need to happen. And if you have a lot of those happening at the same time, you hit concurrency bottlenecks. And also, all the operations that happen in TempDB are logged. So it's all written to the transaction log. And that is for rollback purposes. Right? So there's potential contention here on if you have a lot of concurrent requests using TVPs, and you need to provision enough log I/O. And we know that, for example, in Azure SQL Database, this counts towards your log I/O cap. So if you have high log I/O and you're using a lot of table variables, think about using memory optimized table variables to reduce that log I/O. And when you think about transient data, that is where people often use temp tables. Typical use of temp tables is, well, you have a stored procedure that does a whole bunch of logic, does a whole bunch of business logic, and you use temporary tables as a means to store like intermediate result sets, intermediate results, so you can do further processing based on that. So you create your temp table, insert some data in it, and you do stuff there, right? So this is, again, a table being created in TempDB. Again, allocations will happen, and this is going to be logged as well. So you need to provision all that, right? You need to provision the log I/O. So but that's a lot of work being done for those. Now, the way you would go from that to a memory optimized table variables and memory optimized tables for temporary data, it would look something like this. So memory optimized table variables, they're very easy to start using. Just use memory optimized table types. So in this case, you would send a memory optimized TVP. This memory optimized TVP will get a corresponding structure within the user database, in the memory space of the user database, and there's no logging going on whatsoever. And then if you are interested in some transient data that you want to keep track of, what you do with memory optimized tables, you create at deployment time. That's an important thing to remember. At deployment time, you create a table that is schema only, and then within a stored procedure, you reference that table, you do your work. Right? So it is, again, this table would live in memory of the user database. Advantages are, of course, no tempdb, no disk I/O at all. You remove all contention on allocations. You will also remove contention on any data access, right? And also reduced CPU utilization because of the memory optimized data access and improved latency. And another advantage here specifically for the temp table scenario or temp data scenario from a programmability standpoint is that the schema is actually persisted because these are user tables. They're part of metadata of the user database. So if the database restarts, you don't need to recreate the temp table or anything like that. The table is just there, and you can just use it for your caching needs and for your temporary data needs. I did have a demo prepared, actually, something I already planned on Tuesday. I did not get to it. I also don't have time to go through it today. There is a link, though, to the blog post that goes through the details, and that actually shows, that explains in detail, like what are the patterns for these memory optimized table variables for the temp tables and how to get started, how to implement it. So I would recommend to take a look at that blog post. The final scenario I want to touch on is ETL. So this is where you load data into a data warehouse and you do some transformations along the way. And then there are also quite a few customers who use them. And actually some of the customers that had some sessions, joint sessions at Ignite earlier today and yesterday, Atom and Channel Advisor, they are both leveraging in-memory OLTP for this pattern. So what you typically do for ETL is you have your operational database. You send your data towards your data warehouse, for example, using integration services. This is then loaded into staging tables, and you would use schema-only tables for that to remove I/O, improve data access performance. Optionally, you would do some transformations on that data using natively compiled stored procedures. And finally, you load it into your dimension and fact tables that are probably using column store. So some advantages are that schema-only tables, they remove log I/O for your staging tables altogether. So it reduces the total time taken for your ETL process. And if there is a failure in halfway the ETL process, well, you usually want to restart the ETL process anyway. That's what you usually do. And you have the source data anyway in your operational database. So it's no big loss if the data in the schema-only tables is gone after a failure. And then also you reduce the CPU utilization. So you reduce the overall time of the ETL process with this. Okay, now just to recap before we wrap up. So with in-memory OLTP, it provides a lot of performance benefits, and then also if you are really interested in getting the most out of performance, you want to think about durability. So full durability is the default that you have always known and which you probably should use in all cases. After transaction commit, if there is a failure at any point, your data is just there. But there's also the option of delayed durability if you want to reduce the latency even further, but there's potential for limited data loss. And then we have the non-durable tables, the schema-only tables, which are not logged, and then, of course, only suitable for temporary and transient data. Then you want to consider when you want to use in-memory OLTP. So it's ideal for transaction processing and also transient data scenarios, as we've seen here. If you have analytics, reporting style, look at column store instead. And also, one factor you want to consider is that the performance gains are going to be limited if the bottleneck is outside the database, like the Chatty application we mentioned. And we have seen here a lot of scenarios where in-memory OLTP has shown to offer performance benefits. And it is, of course, not limited to just these scenarios, but these are the scenarios where we have seen a lot of customers get a lot of benefit from the technology. Okay, we have some related content. There's a lot of resources in the slide, so I would recommend you download the slide and review these. And of course, always feel free. Oh, they removed my contact information from the back, so feel free to always reach out to me if you have any questions. I will be here also after the session. Thank you very much.